Project Euler Problem 2. Each new term in the Fibonacci sequence is generated by adding the previous two terms. By starting with 1 and 2, the first 10 terms will be 1, 2, 3, 5, 8, 13, 21, 34, 55, and 89. By considering the terms in the Fibonacci sequence whose values do not exceed 4 million, find the sum of the even-valued terms. Let's make sure we understand the problem statement because I'm going to diverge a little bit from their setup. To simplify, we need to find the sum of the even-valued Fibonacci terms under 4 million. Let's review the Fibonacci sequence. What is the 0th Fibonacci number? By definition or base case, hopefully we can agree it's 0. What is the 1th or Fibonacci at 1th number? Again, by definition or base case, hopefully we can agree it's 1. What is Fibonacci at 2? It would be the sum of the previous two Fibonaccis. Fibonacci at 0 plus Fibonacci at 1 would be 1. Let's do it for 3. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 2 is 5. And so on. And so on. We should have enough now to write a simple Fibonacci function. I'm going to use Python for our language of choice. Let's take in a single parameter, n, to indicate which Fibonacci term we would like to get. What if n was 0? We should return a 0 according to our table. What if n was 1? According to our table, we should return a 1. Can you see a way to simplify our code? Pause if you'd like to try and figure it out. Now, what do we do if n is not 1 or 0? Hint, take a look at our function above. We would sum up the previous two Fibonacci numbers, and we have just written a recursive function. Let's try to make sense of what's going on, and say we wanted Fibonacci at 2. Let 2 equal our n, and let's substitute it in everywhere. Now we'll do some subtraction, and we have more function calls. Fibonacci at 1 will return a 1, and Fibonacci at 0 will return a 0. 1 plus 0 is 1, so Fibonacci at 2 is 1. Let's reset and do it again for Fibonacci at 4. We are starting here at 4, and let's update the ends. Do some subtraction, and now we need to do Fibonacci at 3. But we don't have results for Fibonacci at 3. So that means we need to compute it and run another function with Fibonacci at 3, which calls for a Fibonacci at 2 and a Fibonacci of 1. We do have values for those, so we can substitute them in. If you were paying attention, I did skip a step for simplicity. 1 plus 1 is 2. And now return the value for Fibonacci at 3. And now we can work on the other Fibonacci at 2, which will just return a 1. And yes, I skipped more steps. Now we add 2 and 1 to get 3. And we have our Fibonacci at 4. Let's wipe the screen and do another example. Let's look at the 5th Fibonacci term. So that means we need the previous two terms, 4 and 3. For the 4th, we need 3 and 2. For 3, we need 2 and 1. For 2, we need 1 and 0. 1 and 0 are our base cases, so we can just return those values back up the tree. 1 plus 0 is our f2, and we turn that back up the tree. And we can now work on the other f1 for our f3. f1 is our base case, and we'll just return a 1 back up the tree. Now we have everything we need for f3. f3 is 1 plus 1 and is now 2. We can pass the results of f3 back up to f4 and work on f2. For f2, we need an f1 and f0. 1 and 0 are our base cases, so we can just return those values back up the tree. We have our result for f2 and can now compute f4. f4 is 2 plus 1, which is 3. We can pass up our result from f4 to f5 and work on f3. For f3, we need f2 and f1. For f2, we need f1 and f0. A little bit of cleanup, and f1 is 1 and f0 is 0, and we can return those back up the tree. f2 is now 1, return that back up the tree to f3, and we can work on the other f1 for f3. f1 is equal to 1, and we can return that back up to f3. We can now assign 2 to f3 and return that up the tree. Finally, we can sum the results of f4 and f3 for f5, and we have 5. Notice we do have a lot of repetition here. Specifically, these three branches look exactly the same and calculate f2 3 times. Additionally, f3 here, these two, also do the same thing. What if instead of computing the same value again and again, we create a basic lookup table to see if a value has already been computed and use that instead? When I think of lookup table, I think dictionary. Let's create a dictionary called fibs. Since this dictionary is going to contain computed values, why not pre-compute the results for 0 and 1? Which will let us get rid of our if statement. Now we can just pull the values from fibs and get a key error because our n might not be in there. Alright, so how about we wrap this up in a try except? Okay, so if our value exists in fibs, store it in f, and if it doesn't exist, we get a key error and need to compute the previous fib and store it in fibs. Finally, let's update our return statement. And I don't like what we have. Did you know there's another way we can get a value from a dictionary? Get. With get, we don't need the try except because if a key isn't in our dictionary, we'll get a none type. So we would check if f is none, and if it is, compute it. But wait, if you have a newer version of Python, we can make our code even more unreadable. I present the walrus operator. It allows us to do an inline assign and use the variable at the same time. Anyway, what we just did is memoization. Compute values once, save it, and if we need it again, look it up. I do have one more thing to show off. Here's the original function before we memoized it. And here's what you need to add to use the built-in memoization function from functools. Write our own memoization or use a built-in wrapper. They both work the same, but the built-in one is more robust and obviously is easier to use. Let's go back to our mess and see what memoization does for us. Let's start with the green circles. Instead of recomputing, we perform a lookup and the additional computations go away. Now let's look at our yellow circles. All of these duplicate computations go away, and we get a significant speed up. If you'd like to time it for yourself, here's some starter code. Also note that if you're using the newest version of Python or Apple Silicon, you may not see much of a difference because of how heavily optimized they are. Before we tackle the even values under 4 million, I'd like to talk about another optimization we can perform. Every time we call our Fibonacci function, we take up space on the stack. Let's demonstrate by calling F5. F5 needs to call F4, but before doing so, we'll need to store the state of F5 in the stack. Now we can call F4. F4 needs to call F3, but needs to store the state of F4 before it can call F3. Now we can call F3. F3 needs to call F2, but needs to store the state of F3 before it can call F2. Now we can call F2. F2 needs to call F1, but needs to store the state of F2 before it can call F1. Now we can call F1. F1 is our base case, and a 1 is returned to F2. We return to F2 by popping F2 off the stack. Now that we're back in F2, we need to call F0, but we need to store the state of F2 before we call F0. Now we can call F0. F0 is our base case, and a 0 is returned to F2. We return to F2 by popping F2 off the stack. Now that we're back in F2, we can return our result to F3. We return to F3 by popping F3 off the stack. Now that we're back in F3, we need to call F1. Before we call F1, we need to push F3 onto the stack. Now we can call F1. F1 is our base case, and a 1 is returned to F3. We return to F3 by popping F3 off the stack. Now that we're back in F3, we can return our result to F4. We return to F4 by popping F4 off the stack. Now that we're back in F4, we need to call F2. Before we call F2, we need to push F4 to the stack. Now we can call F2. F2 was previously computed and cached, so we're doing a lookup versus needing to run F1 and F0 again. So we can just return our saved value back to F4. We return to F4 by popping F4 off the stack. Now that we're back in F4, we can return our results to F5. We return to F5 by popping F5 off the stack. Now that we're back at F5, we need to call F3. Before we can call F3, we need to push F5 onto the stack. Now we can call F3. F3 was previously computed and cached, so we're doing a lookup and we can just return our saved value back to F5. We return to F5 by popping F5 off the stack. And we have our F5, which is 5. We did a lot of jumping back and jumping forward. That was exhausting. There must be an easier way. Is there another way we can interpret the Fibonacci sequence? Blue plus red equals violet. Blue plus red equals violet. Blue plus red equals violet. Are you thinking we don't need to even use these green arrows? Instead of starting from the right, we start our Fibonacci sequence from the left? Let's work on writing a new Fibonacci function. Here are the first few Fibonacci equations. If we kept going, we'd run out of variables. Let's try reusing some. Our first real computation is at F2. f2 is the sum of the first previous and the second previous variables. Let's update their names. If we wanted to compute f3, we would need to first update our previous variables. The number 1 was stored in second, and now we're moving it to first. Since we want to calculate f3, we need to update second with the value we got from f2. And now we can get f3 by adding the first and second previous numbers. Let's update f2 and f3 to be some nth reusable variable. And I think we have a viable loop. This part, that is. Let's do some cleanup and shorten our variable names. Let's turn this into a function that takes an argument that would be the desired nth term in the Fibonacci sequence. The last 3 lines are going to be looped over again and again somehow. Would you agree we need to start with 2 because we originally started computing the sequence at f2? Would you agree that we need to do this loop n times, n coming into the function from the top, that is? Would you agree that we need to add 1 to n because range stops at up to but not including our last number? Would you agree that we don't need to use the value produced by range and indicate that with the underscore? Would you agree that we can use tuple packing and unpacking to simplify the first 2 lines of our function? Would you agree that our return value should be SP, the second previous? And finally, would you agree that the function parameter n is confusing with the use of that temporary variable n inside the for loop, and we can get rid of that temporary variable using tuple packing and unpacking? And this is tabulation, and the second part of today's dynamic programming. And by the way, this function runs in constant space, unlike our recursive function. Now we're ready to take a look at the even-valued Fibonacci terms. They're right here. And they look super suspicious to me. Why is that? Because it looks like every third number in the sequence is even. Wouldn't it be great if it was? Want to test it out? Let's do Fibonacci at 4 million, add this if statement to check if one of our values is even, and if it is, print it out. And I hope you didn't run that because we just asked for the 4 millionth Fibonacci term, not go up to a result that is less than 4 million. Your terminal would have never stopped printing out numbers. We need to add another check to see if our term is less than 4 million, else break out of our for loop. From a quick look at our output, it does look like even numbers only appear every 3 terms, but this isn't enough proof to know for sure. What is enough proof? A proof. But I don't like the state of our current program, and I want to fix that first. Let's update our definition of n. Let n be our maximum term value. Then let's trade out our for loop for a while loop. The while will break our print statement and our under 4 million check, so let's get rid of those. Finally, how about we turn this into a generator so we can see all of our even numbers versus returning only the largest term under 4 million. Let's run this to see what we get. And here's our result. Obviously, we can just pass this to sum instead of list, but there is one more optimization we can do to make this the fastest, most optimized solution of all. But first, that proof. What do we need to prove? Based off of this observation, prove that every third Fibonacci is even. So where do we begin? Let's look at how we compute f of n's. Let's evaluate everything and take a closer look at the specific rows we want. We want to figure out how we can generate these numbers, since they will generate our first or 0th term 2. The next term we want is 8, and then 34. For our first line, what do we do if we had an input of nothing to get an output of 3? Nothing plus 3. Math checks out. Let's propagate that down and test the new input, say 1. 1 plus 3 is not 6. What do we need to do to make our output equal? Multiply our input by 3, perhaps. 3 times 1 plus 3 is 6. All right, looks good. Let's update our 0th input with our updated equation. Yep, math still checks out. Let's try an input of 2 and apply what we have so far. Looks like we've found a pattern to generate inputs for getting every third number. Let's update our proof statement. Now, what does it mean to be even? An even number can be represented by multiplying 2 to some n where n is an integer. Let's pick an even result and try to generalize what makes up that even. These rows look good. Let's look at only the things we want to generalize. Let's add our 3k plus 3. F4 and F5 don't quite match up. Let's fix that. A quick note, for this example, our k would be 1. Much better. Let's copy our F4 and F5 into our F6 row. Let's include the mathematical definition of odd and even. We should now have enough to begin working on our base case for an informal proof by induction. We need to show that this is equal to this for some number k and the next number after k, which is k plus 1. Let's show a given k is even by substituting our F4. Since the result of f3k plus 2 is an odd number, we can put in 2n plus 1 in its place. The same goes for f4. Let's remove the parentheses, add them up. We get 4n plus 2. Let's factor out a 2. 2 times some number means our result is even. Let's reset and prove that the next number after k also works. Let's swap out k for k plus 1, and let's remove some of the f's. Let's simplify. Let's substitute. Let's add. Let's factor out a 2. And that's the end of the proof. We can now confidently say that every third Fibonacci number is even. Let's take a look at our last program's results. Currently, to get our even values, we need to know the previous 2 values. Wouldn't it be nice if we could do the same here, as in use our previous even values to get the next even value instead of computing previous odd values? Here too, and so on. Let's bring back our first 9 Fibonacci functions. Could we write f9 in terms of f6 and f3? Let's try it out. f8 is just f7 plus f6. f7 is just f6 and f5. Let's clean up a bit. Let's only swap out one f5 so we can combine f4 and f5, else we would have needed to backtrack. Simplify one more time, and we've done it. We wrote f9 in terms of the previous 2 even numbers. Let's apply this to our latest program. Let's update our while loop. And don't forget, we also need to update our first and second previous starting values. Finally, we can remove our even check. Let's see what our results are. Uh-oh, our output doesn't match our previous results. That's because our initial values are now part of our desired results. Let's fix that. Let's try again. Much better. Now to sum our result. This has been the bestest, most optimized, fully explained Project Euler, Problem 2. Thanks for watching.